Okay, it's 8 o'clock. So I guess it's time to get started. Remember, you have your exam 2 Friday. We'll do it the same way we did the exam 1. And that means that I have to be able to see all of you on video camera, okay? If I can't see you, I won't take your exam. And you can come and take it on campus later. Yeah, I decided the time for that because I'm only going to do it once. Also, yeah, the practice exam is posted now. We will review on Thursday. Today and tomorrow, we're going to talk about curve sketching. And what I'm talking about now, what I've been talking about for several days now, is not going to be on the exam. We're talking about some new material now. Any questions? Okay, let's get started. Oh, I didn't start recording. Go back. Okay, now. Okay, we started talking about this yesterday. I don't think that I got even an example worked, but we'll work plenty today, okay? The increasing, decreasing test. If you have a function f and it is positive on an interval, it has a positive derivative on an interval, that's going to mean that f is increasing on that interval. Okay, we talked about what increasing and decreasing meant. Basically, let's see. So let me just put that definition up before. F is increasing on an interval I. When x is less than y. Both of them in your interval. Then f of x is less than f of y. And okay, so increasing, going up. It's decreasing if f goes down on the interval. If when x is less than y in I, f of x is greater than f of y. So picture, okay, and somebody just entered. Okay, Yeah, so a picture, that's a decreasing function. Okay. And we can use, according to the increasing decreasing test, we know that our derivative is positive, then we can conclude that f is increasing. Let me prove that for you. I'm going to prove this statement, the first one. The second one, you do pretty much the same way. And I'm going to use the mean value theorem. Okay. So suppose I'm going to do the increasing statement. Suppose f prime of x is greater than 0 on the interval I, which means, okay, for each x in the interval I. When I say it's increasing, oh no, that's what I mean. Okay, then well, suppose I just pick two numbers in the interval. Two numbers, x1 and x2, and I may as well call the smaller one x1. Okay, then the mean value theorem says that there is some number c in the interval, actually open interval, from x1 to x2, such that f prime of c, is equal to f of x2 minus f of x1 over x2 minus x1. Okay, so I'm using the mean value theorem there. But what do we know about f prime of c? Well, f prime of c is in x1, x2, and x1, x2, that the open interval from x1 to x2 is in this interval I, bigger interval. Okay, so C is in I, and remember we're assuming that f prime on the whole interval is positive, so f prime of C in particular is a positive number. Okay, so f prime of C is positive, and x2 minus x1 is also positive. Well, then if f prime of C is positive, okay, this number is positive, this number is positive, and in fact, actually, I can just say f prime of C times x2 minus x1 is equal to f of x2 minus f of x1. Well, this is positive, positive, positive times positive is positive. And that means that, say that, okay. Okay, so f prime of c times x2 minus x1 is positive. And well, if the left-hand side of the equation is positive, the right-hand side has to be too, because they are equal. Ugh. Trouble writing this morning. This is also positive. Okay, but if f of x2 minus f of x1 is positive, well, that means that, okay, if I add f of x1 to both sides of the inequality, that means that f of x2 is bigger than f of x1. And thus the theorem is true. Okay, that's what we wanted to show. That given an x and a y in the interval with, well, we call it x1 and x2, okay? We picked any 2 points in the interval, call the smaller one x1 and the larger one x2, then f of x1 is less than f of x2, so f is increasing. And that's what we wanted to show. So it's an easy little proof, almost obvious. But if we know that the derivative is positive, we can conclude that the function's increasing on an interval. Very similar manner, if it's negative, if the derivative is negative, the function is decreasing on that interval. Any questions? Okay, let's work some problems. See if we can figure out what, well, we're going to start using this to sketch curves. And the second derivative also tells you information about your function. I'm actually not going to get into that today. I'll wait and get into it tomorrow. It tells you about something called concavity. First derivative tells you where your function is increasing and where it's decreasing. Okay. Too many pillows on my couch. Let me get rid of some of them. All right. So here's a problem. I want to find where the function f of x equal to 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and where it's decreasing. And to figure that out, I need to know where the derivative is positive and where it's negative. Okay, so we need the derivative, and f prime of x would be 12x cubed minus 12x squared minus 24x. Let me go back and check to make sure. Okay, 4 times 3 is 12. Drop 1. Okay, 3 times 4. Drop 1 power. All right. Okay. Well, I want to know where f prime is positive, the intervals where f prime is positive, and the intervals where it's negative. And I also want to know the places, well, let's see. Yeah, I want to figure out where it's positive and where it's negative. Well, so where does it change from positive to negative? That's a key question. To change from positive to negative, it either has to go through 0 or it doesn't exist. So to find where f prime of x is positive and where f prime of x is negative, I need to find where f prime of x is equal to 0 and where f prime of x is not defined. You need to know those things because the places where it's equal to 0 or not defined are the only places where it can go from being positive to negative or vice versa. Okay, well, f prime of x here always exists. So I'm not going to get any, yeah, actually, I'm looking for the critical numbers, okay? We talked about that last week. We're looking for the critical numbers. The places where the derivative is 0 are not defined, but the function is. Actually, you flat out want to know where f prime doesn't exist. Even if an x is not in the domain, so f of x doesn't exist, you can still have your derivative change at such a change from positive to negative at such a number. So I want to know more than just the critical numbers. Okay, that's way too much detail. But so for this function, the derivative always exists. So it's going to be where the derivative is equal to 0. F prime of x is equal to 0. That means I want to know where 12x cubed minus 12x squared. Oh, did somebody just come in?
Yes, ma'am.
Okay, let me go back and let them in. A little bit late to class. Okay. Minus 24x is equal to 0. Okay. Well, here's where you want to try to write your derivative as a product, okay, if possible, because it makes it easy to find these roots. Easier, I should say. Yeah, that's what I'm looking for. I'm looking for the places where 12x cubed minus 12x squared minus 24x is equal to 0. Okay, so I'm going to take this and try to factor it. Well, I can factor out a 12, and I can factor out an x. 12x, okay. And out of the first term, that's going to leave me with x squared. Out of the second term, just x. And out of this third term, minus 2. Okay, and then I want to try to factor that. What's the quadratic? So even if I can't factor it, I can always use the quadratic formula. But I bet you I can factor this one, because it came out of a book. And they're all carefully selected to work out fairly nicely. In real life, that doesn't happen much. Okay, so minus 2x. I think that works. And the nice thing about writing it as a product, because we can use the fact that when you have a times b equals to 0, that means that a is 0 or b is 0. Okay. So that says then, and that's where what I want to know where these are 0. That says if one of these factors is 0, the whole thing is 0. So from the first factor, the 12x, I get x is equal to 0. Okay. From x minus 2 equals to 0, I get x equal to 2. And from x plus 1 equal to 0, I get x equal to minus 1. So I've got 3 places where the derivative is 0. Okay, let me draw a number line so we can visualize. I've got identified 3 numbers. These are all critical numbers. And I'll call that 2. Those 3 numbers are the only places where f prime of x is equal to 0 or f prime of x is not defined. Here, they're all equal to 0. So a change cannot occur between these points. And outside the points too. I've got all the places where a change from positive to negative or negative to positive can occur. And that means that it's the derivative, let's say I pick number over here. Oh, let's see. I'll pick it. It can be any number less than minus 1. Well, how about minus 2? All I want to know is f prime bigger than 0 or less than 0 at minus 2? At minus 2, well, let's check. At minus 2, 12x would be negative. I'm just going to keep track of negative or positive. At minus 2 minus 2 minus 2 is minus 4. That's negative. And at -2, -2 plus 1. -2 plus 1 is -1. That's also negative. Okay, so a negative times a negative times a negative is a negative number. It's negative on that interval. The derivative is negative on the interval. F prime, it's, yeah, on that entire interval, F prime is either positive or negative. We found out that F prime of -2 is negative. Therefore, F prime at any number in that interval is going to be negative. And that means that the function is decreasing on that interval. Okay. So I'm going to draw an arrow down. Function is decreasing there. Okay. What happens between -1 and 0? Well, just going to pick a number in between. How about -0.5? All I want to know is positive or negative, okay, for the derivative. At -0.5, 12x would be negative. At -0.5, -0.5 minus 2 is -5/2. That's -2. At -0.5, -0.5 plus 1 is positive. So I have minus times minus times plus. That's going to be positive. And that means the derivative is positive on the entire interval and the function is increasing. Okay. Draw my arrows to indicate that. Between 0 and 2, say I look at 1. All right, put 1 into the derivative. 12x would be 12. 1 minus 2 would be negative. 1 plus 1 is positive. Positive times positive is negative. So the derivative is less than 0, which means the function is decreasing over there. And I've got one more interval to check. Okay, well, 3 would work over here. 3 is bigger than 2. That's in the interval. And now, well, everything's positive. 12 times 3 is positive. 3 minus 2 is positive. 3 plus 1 is positive. That's positive, which means that the function is increasing on there. Okay, so what do we have? Let's write it down. We have that f is increasing on, okay, the interval from -1 to 0 and the interval from 2 on up. F is decreasing on -infinity up to -1 and on the interval 0 to 2. And so I know that, and I also know something else. If the function goes from decreasing to increasing at -1, okay, and I've got a little low point there, all right, is decreasing and then it starts increasing. So it's got a local minimum at -1. Sometimes it's called a relative minimum. I did define those terms last week, which I wouldn't hurt to, okay. It's a local minimum if I'll write it down in a minute. Okay. It has a local minimum, and the local minimum is f of minus 1 at minus 1. Okay, and well, what is the value for f of minus 1? I have to remember my function. F of minus 1 would be, it helps to write the function down first again. 3x to the 4th minus 4x cubed minus 12x squared plus 5. Okay, so f of minus 1 would be, okay, minus 1 to the 4th is 1. Minus 1 cubed is minus 1. So it's minus 1 cubed, I'll write it. Okay, there. Minus 1 squared is plus 1. So that gives us 3 plus 4 minus 24 plus 5. So 7 plus 5 is 12 minus 24 is minus 12. The local minimum at minus 12.
Do you mean for the negative 24, shouldn't that be just negative 12 since x is negative 1?
Absolutely. Thank you. Okay. Thank you. Okay. Where did I get the 24 from? Who knows? Okay, minus 12. No. Okay, wait a minute. So it can't give me 0. Okay. Oh yeah, of course it does. All right, yeah, that's possible. F of minus 1 is 0. And that's so that, okay, there. There. Okay, so we have a local minimum f of minus 1. I'm going to write it up here. It happens at minus 1, but the local minimum is 0. Okay. Likewise, well, okay, at 0, it goes up and then down. So you have a local maximum at 0. F of 0, and let's see, there's my function right there. That's pretty easy to compute. That's 5. Okay. And it's got another local minimum, right? Because there's a change here at 2. It's going down and then it's coming back up. So we've got a local minimum that happens at 2. Local minimum, right? F of 2. I have to compute it. Okay, arithmetic, but okay, let's do it. 3 times 2 to the 4th is 16. Minus 4 times 2 cubed is 8. Minus 12 times 4 plus 5. Pretty large number. Okay, so 48. That's 48, and that's 48. So they add out. So that leaves minus 32 plus 5 is minus 27. Okay. And okay, questions first. Any questions? Well, let me remind you, first of all, local minimum means that it's the lowest point in some interval. Okay, so let me just write that down. F has at the number C if for some interval I containing C this is just a quick review of the definition. For some interval containing C, F of C is less than or equal to F of X for each X in I. So it doesn't have to be the smallest F value in the whole, over the whole domain, just over some interval. And likewise, F has a local maximum at C if for some interval I, and it's open interval. Okay, must be open. No intervals that contain just one point. From some open interval I containing C, F of X is less than or equal to F of C for each X in I. Well, we have this information, actually a pretty good bit of information here about this graph and this function. The F decreases until it gets to X equal to -1. Then it increases until it gets to 0. So it's going down, going up, starts going down again, and it goes back up. Okay, it's also a polynomial, this function, and that means that as you go to infinity, in either the positive or the negative number, or the positive or negative directions, F goes to either plus or minus infinity in those directions. No horizontal asymptotes. Okay. So a rough sketch of the graph we can get right now. We have some important information. Okay, let's see. Why don't I write down my values? Okay, so F of -1 was 0. F of 0 was 5. Those were my local minimum, maxima. F of 2 was -27. And I know it was down, up, down, up. Yeah, basically. Okay. That's just so I have to go way back up here to, yeah, I'm thinking about this. All right. Okay. Well, that minus 27. Okay, I'm going to call that minus 27. And then 0. Of course, this is my x-axis and this is my y-axis. Call that 5. Okay. F of minus 1. And then I'm not doing this to scale. F of minus 1 is 0. So this is actually a point on the curve. F of 0 is 5. That's a point on the curve. And F of 2 is minus 27. That's a point on the curve. Notice that when I'm actually getting points on the curve, I go back to the original function. Okay. That's where all the points on the curve comes from. Okay, but what have I got? F is decreasing over here. Then F increases. Up to, oops, doesn't go down below 0 there. Goes back up to level 5, and then it starts decreasing again. And then it starts increasing again. So that's a very rough sketch of the curve. And we got all of that information about the function from the first derivative. Questions? Okay, let's try another. And how am I doing on time? Okay.
Hello.
Someone said something?
Yeah, hey, I have a question.
All right.
Could we go back up to your number line?
Number line, yes. Okay, right there.
Can you go higher just a little bit more?
Okay.
All right. So all these, all your writing in red, you did a lot of that in your head, and I just want to clarify. We're working with our intervals in here. Is that what we're plugging all those
Yeah,
numbers in?
yeah. Since we found all the places where the derivative could be 0, right?
Okay.
We found all the places where it can go through where it is 0. That means that in between those places, the derivative's either positive or negative. Because if there was, yeah, the places where it's 0 are the only places where it can change sign.
Right. So all, like, for instance, the first set of the first interval was negative, negative, negative. Therefore, it's a negative. So therefore, it's decreasing. But what was it that you did? What was the math that brought you to all those negatives?
I looked at, okay, the derivative up right here. I have it written as a product. And okay, and I know that when I have a product of things equal to 0, that means that one of those things has to be 0.
Right.
Okay. Oh, but that's not. Okay, that's beside the point. How do I get this?
Yes.
Well, I picked a number in the interval from minus infinity to 1. Any number will do. And
Okay.
in fact, pick it so it's easiest for you. Okay, so I picked out minus 2. And then I look at what the sign of each of the factors is at minus 2. Okay, so at minus 2, let me just write it down here. At minus 2, I get, okay, 12 times minus 2 is minus 24. And then minus 2 is minus 4. So I'm looking at this, right? And then minus 2 plus 1 is minus 1. Okay, well, I don't really need to know what those numbers are. I just need to know whether they're positive or negative.
Oh, okay. So you plugged in -2 to this function up here, the 12x.
You're right.
Where we got it. Okay, I got you.
Okay. Yeah, and
so I don't really have to do all that arithmetic. I just want to know whether that number is negative or positive. Well, if it's minus, 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 and that's why I've got three little signs, because I've got three factors. I'm checking each factor.
So you did the same thing with the other interval. You just plugged in negative half to the 12x and the x minus 2 and the x plus 1.
Right.
And so on and so on. All right, I got you.
Okay.
Thank you.
That was a good question, actually. Okay. Anybody else? Let's see. Well, now I'm getting really short on time. Do I have time for another problem? I don't think so. Okay. Well, it's almost 10 minutes. Let's at least start one. I'll pick up here tomorrow. Okay. This is a little bit different. This is one involving a trig function. We want to find the local minimum and maximum values. Of the function g of x equal to x plus 2 sine of x. And actually, that function has domain all the reals, but let's cut it down at least to start with to just one interval. Okay, now we already talked about how to find the absolute maximum and absolute minimum. That's a little different. We do have just a closed interval here. Notice that, okay, going back to this function. This function, well, this function that just worked, it does have an absolute minimum, and in fact, it's minus 27, but it has no absolute maximum because it goes up forever here. All right, it's a polynomial that has to. And that's because, well, that does not contradict the extreme value theorem. The extreme value theorem assumes that your function is continuous on a closed finite interval. Well, there's nothing finite about the whole real line. Okay, it's infinitely long in both directions. So, well, whatever that means. Okay, so it's a different question when I ask you for an absolute maximum and an absolute minimum than the local minimum and maximum. So for this, again, what I want to do is take the derivative and then find all the places where the derivative is equal to 0 and where it's not defined, because then I will know when g prime is positive and when it's negative. I'll know the intervals on which g prime is positive and the intervals on which g prime is negative. Okay, so that means I need g prime. It's just 1 plus 2 cosine of x. Okay, and g prime is always defined. So no critical numbers where the derivative doesn't exist. It always exists. So I want to know where g prime is equal to 0. That's going to be where all my critical numbers are. Okay, so set it equal to 0. And that says that minus 1 is 2 cosine of x. That minus 1/2 is the cosine of x. Where is the cosine of x equal to minus 1/2? Okay, and think about my unit circle. The cosine is negative for anything on that side, right? Because the cosine's x values. So I'm looking for angles in the second and third quadrant that satisfy the cosine of that angle's minus 1/2. Where's the cosine of x equal to 1/2? Anybody remember their special angles, which you should know? Where's the cosine of x equal to 1/2? Let's see, what's a
We got 2 pi over 3.
yeah, 2 pi over 3. All you gotta do is remember this little triangle. Okay. And actually, yeah, I want to know where cosine of x is equal to 1/2. Well, in fact, I got that labeled wrong. Okay. That would be sine of x there. Well, the triangle, okay. This is pi over 3. Wait a minute. Nope, 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 nope. Nope, nope, okay. That angle is pi over 3 right there, that angle. This angle is pi over 6, right? So yeah, okay, I'm turning my iPad around. You can't see that, but okay. The cosine is 1/2 means that I'm looking at the adjacent as being, to this angle right here. Okay, that's 1/2. Then that's pi over 3. 2. Okay, yeah, this is pi over 3. But of course, that's in the first quadrant. In the second quadrant, the corresponding angle would be means that x is 2 pi over 3. And what about in the third quadrant? There's one there too.
Would it be 4 pi over 3?
Yes. Okay, well, we'll stop there. I've got these, so I found so far the critical numbers. I have not answered the question yet about the local minimum and maximum values, but we will pick up here tomorrow. And yeah, finding the critical numbers, that's a good start. Okay, so class is over. If you want to hang around for a minute and ask some questions, that'd be fine. But otherwise, you can leave.